Students, last class we discussed about the packing efficiency of different type of the solids. Today we will discuss regarding close packing of the solids. So let us look here, sir. In close packing of we have to discuss today regarding close packing in the crystalline solids. So let us look here, sir. In these crystalline solids, the constant particles may be atoms, or ions, or molecules. Let us consider these particles are the atoms. So whenever we have to make arrange, the crystalline solids has to be arranged. The atoms are found to be arranged, and these atoms are arranged in different manners or different ways. While we have to arrange these crystalline solids by taking the atoms as a constant units, we can arrange them three-dimensional way. First is we can say arrange in one dimension, and second one is two dimensions, and third is our three dimensions. So we can keep the solids in these three directions: one dimensions, two dimensions, and three dimensions. But actually, regarding the arrangement of the solids, in real case, only it takes place in three-dimensional arrangement. But this three-dimensional arrangement takes the shapes of two dimensions. So let us we have to go one by one, and now last we have discussed regarding three-dimensional space. So let us say one-dimensional space. If a solid has to be considered just like a sphere, while we have to arrange them or keep it systematically managed in one dimensions, then what will happen? These spheres they will continually attach to one another and will form the lines. They will continually attach and they will form the lines, and these lines will continue. So what will happen, sir? In these one dimensions, each sphere is found to be contact with two other spheres. Those are closely proximate to you. So let us consider this sphere. So if we consider, then these spheres is in contact with this one and this one. That means we can say this particular sphere has two neighbors. So we can say coordination number of this particular sphere is 2. Coordination number of this sphere is 2. Number of the sphere is 2. Coordination number of this sphere is 2. So this is the case that involves in one-dimensional cases. Let us here to come regarding, actually in case of a solid, any solid, this don't found to be happens. Let us now here to come two-dimensional way of arranging. In case of two-dimensional arrangement, what will happen? The spheres are found to be arranged according to length as well as breadth. Okay. So let us we have to see the diagrams of two-dimensional arrangement of the solids. In case of this two-dimensional category, we have to see there are two type of packings we arrange. One is you can say square close packing, and other is we can say hexagonal close packing. So let us look here. So you have to see here, so two types of packing will happens in case of square close packing. In case of the two-dimensional way of arranging, square close packing and hexagonal close packing. Its name is given square close packing because whenever a particular sphere is attached with the other spheres, if you connect the other spheres centers, then it will come look like a square. That's why it is known as a square close packing. Similarly, if you in hexagonal close packing, if you take a particular spheres and you will surround the centers of the rest spheres, then they will come the 6 spheres and they look like just like a hexagon. That's why we can say hexagonal close packing. Let us look here. So in case of square close packing, we have to take the solids that is the spheres, they are present in one line, and the second layer we have to see found is in above of it, exactly like the above of it as the first layer. As the first layer, the second layer has to be continued, and third layer will continue above that, and fourth layer will continue above that. So similar type of arrangement is found to be obtained. So let us look here, sir. Here in this type of pattern, so what will happen? This first layer, second layer, third layer, fourth layer, all layers are found to be arranged vertically as well as horizontally in the same fashions. So if you select any one sphere, let us I have to select this spheres, and this sphere is in contact with these four spheres, 1, 2, 3, 4. So if we connect or draw link with all the centers of these four spheres, just you can see it comes like a sphere. That's why this type of pattern we can say square close pattern. Hence it is we can say square close packing. So in case of the square close packing, we see there are many empty spaces is found to be formed. That's why you can say in this type of packing the efficiency is found to be very less, because many spaces of voids is found to be left over, and this is known as a square close packing. Now let us, we have to come the hexagonal close packing. Look here, sir. In case the hexagonal close packing, what will happen, sir? Again, sir, here what will happen, sir? The spheres has to be arranged. While they are arranged, in this case, the fashion is found to be different at that of the square close packing. What happens here, sir? It has to be taken the first line, the spheres, and the second line is found to be depression of the first layers, so that maximum area of the solid is found to be occupied as compared to square close packing. So in case of the hexagonal close packing, the depression or the voids that is formed in the first layer has to be occupied something more as compared to previous one, and once again the third layer that has to be formed over the depression of the second layer. That means the third layer will come exactly that of the first layer. Again fourth layer, again on its depression fourth layer will be made up, so it will again come to the second times. So you can say if the first layer is A, if you say second layer is B, then the pattern will come A B time. Just look the picture, so you can clearly understand. So see, this is the spheres, they are arranged in horizontally. That is the first layer, okay. And when the second layer will form, so the spheres will be present on the depression of this first layer. So let us look here, sir. The spheres will come at this place. All the depression places will be taken by the second layer. Similarly, whenever the third layer will come, this layer will be A. Similarly, when the third layer will come, it is again the spheres will come on the depression of the second layer. So it will be just like the previous layer of the first layer, that is A. It becomes the layer just A. Okay. So once again, whenever the fourth layer we have to go, the fourth layer, the spheres has to be occupied the depression of these two layers once again. So it will once again will come like this. So this will come this layer like this. So you see the arrangement will come just like first is A, second B, next A, next B, next A, next B, just like it will going on. So if we randomly select one sphere, let us look here, sir. If we take a sphere, just I take this spheres. Now you see these spheres will contact with how many spheres? 6 spheres. 1, 2, 3, 4, 5, 6. Now I have to take in the centers of the spheres. Each sphere's center I have to take in. So and now I join all these centers. So you look here, this looks like a hexagon. Okay, because it looks like a hexagon, so its name is given hexagonal close packing. And this hexagonal close packing, if we compare regarding square close packing, whose efficiency will remains around 50%, but in hexagonal close packing the efficiency is around 60%. So out of this close packing arrangement, we can say the hexagonal close packing is a better close packing where more space has to be occupied and less space or board has to be left over. So in the efficiency, why we have to consider is the hexagonal close packing is found to be better as than that of the square close packing. So students, now we have to know what is the one dimension arrangement and what is the two dimensional arrangement. Next we have to come three dimensional arrangement. Actually, in case of the crystalline solids, those we have to found, they are exclusively found in the three dimensions. The question is why? Because if it is a one dimension, it's just like a line. So no solid will form as a line. Okay. Similarly, if you come to two dimensions, no solid will come just like a sheet. If it is a two dimensions, what will happen? Only length is there and breadth is there. That means one slit line. But a solid is not a slit line. It may be a cubical form, rectangular form, hexagonal forms. So in any form, so it has to require three lengths: length, breadth, and height. Three parameters. So actually speaking, in case of the all crystalline solids, we have to form the three dimension type of arrangement. So why we have to discuss regarding three dimensional of arrangement? In this three dimensional of arrangement, once again, you see, there are two layers already comes. One is the length form and another is the height form. Okay. So now you see, whenever you have to go three dimension, what will happen? One layer will come above of it. This is already base layer, length and breadth. When you go to the third layer, it will come above of it. Okay. So whenever we will go to the above of it, then we have to see length is there, breadth is there, next height will going on. So whenever height will going on, the next spheres will occupy on the above of it. Do you clear? Whenever we have to occupy above of it, once again there will come two types of the arrangement. Two types of arrangement. How is it you see? One case, what is the arrangement already present here? Same arrangement has to be repeated. Same arrangement. What is the arrangement? Same type of arrangement you have to get. Because you see, in three dimensional cases, also we have to make two types. One three dimensions involving square close packing. Square close packing. And another three dimension involving hexagonal close packing. Hexagonal close packing. So let us look here, sir. We have to make it three dimensions. But why we are making the three dimensions? Already it contains your two dimensional structures. So based upon the two dimensional structures, three dimensions, so we have to categorize into two types: square close packing type and hexagonal close packing type. In case of the square close packing type, it is very simple, because you see in square close packing type, just like the earlier cases, there is a row of spheres, okay, and it is surrounded above of it, okay. So you see, this is already two dimension is there. This is a two dimension. So whenever we have to keep the third sphere, then the third sphere just will superimpose this layer only. So what will happen, sir? What is the arrangement in horizontal manner as well as vertical manner? The third layers, okay, the third dimensions will come just above of it, simple above of it. That means you see, this is the first layer. In this layer only, exactly in a horizontal manner as well as vertical manners, we can keep the spheres just above of it. So what will happen? Same spheres will be repeatedly come at these places. Same spheres and same arrangement it will be going on. Okay, so you see, this is another layer above it. When the third layer will come, then it will come once again. So if we repeatedly go, then the arrangement will come A type, because same type of arrangement has to be happening in case of the square close packing, that with a three-dimensional structure. Okay, so that is a case involving square close packing in a three-dimensional structure. Now we have to come three-dimensional structure involving hexagonal close packing. Okay, so you see, in case hexagonal close packing, what will happen? So you see, this is the structure just look like a hexagon, and here coordination number is found to be 6. Okay, and in hexagonal close packing also we have to get two types. One is HCP and this CC. This hexagonal close packing also involves two types, HCP and CC. HCP means simple hexagonal close packing, CCP cubic close packing. So now you have to see what is the difference between these two cases, hexagonal close packing and cubic close packing. Now student, you see there are voids is found to be formed. Voids. Look here, there are voids is found to be formed. There are two types of the voids is formed. See, one is below, another is above. Below, above, below, above. Okay, just A, B. We can say one is A, another is B. B, A, B, A, B. Okay, so now you see A, B. Okay. So in this AB, what we have to see in case of the AB, it is one type of words and it is another type of words. One type of words, another type of words. This is A, B, A, B, A, B, A, B. Just like it will come. Okay. Whenever we have to keep the third layer above of it, what will happen is the third layer will place above of it in the voids. In the voids of A, in the voids of A, third layer will be placed. Okay. So whenever in the voids of A, third layer will be placed, above layers will go in place, then the structure will come, that is also what we say hexagonal close packing. Okay. So once after, if we go to the third layer above of it, we will again get two type of words, that is C and D. Above that we will get two type words, C and D. If once again that fourth layer will occupy the spheres, then another type of arrangement will come, and then what will happen, sir? The arrangement is found to be different. Let us look here, sir. That means in simplified way we can say, in these two arrangements, HCP and CCP arrangement, what is basically difference? You see, in case of HCP arrangement, it will come, the arrangement will come just like you see. If the first layer A, second layer B, first layer A, second layer B. That means what is the first layer? Second layer will come different, and the third layer will become exactly to that of the first layer once again, and the fourth layer will come once again similar to second layer. Then fifth one will become similar to third and one. That means one will go even series, other will go to the odd series. Okay. So whenever we will go even series and odd series, what will happen, sir? In even series and odd series, the arrangement is found to be formed. So you can say basically it is a three dimensions. But if you go to the layers will come two types, A, B, just like this the layers will form. So it is, you have to say, HCP type of arrangement. But what will happen in CCP arrangement, it is something different. What happens? First layer will come A, second layer will come B, and third layer will come different. That means third layer will be placed on the verts of the second layer. As a result, once again it will become another type of the layer, that we can say C layer. Okay. So you see in the CCP arrangement, we will get the pattern A, B, C. So after ABC, next one will go exactly same way. We will get the pattern ABC. So let us look here in this two type of patterns. In case of SCP, we have to get AB pattern, and in case of the CCP type pattern, we have to get ABC just like this. So you see here, in case of the hexagonal close packing, we have to obtain two types of the arrangement. One is a hexagonal close packing arrangement SCP, and is a cubic close packing arrangement. And for example, if you take the element just like calcium, strontium, beryllium, all will undergo this SCP type of packings. But if you take gold, platinum, zinc, these metals, they will go to CCP type of packing, that is a cubic close type of the packing. So now you see, in case of the crystalline solids, what will happen, sir? We have to found the close packing of the solids, and that is found to be happening in three-dimensional way. And in this three-dimensional way, once again we have to see two types. That one involves square close packing and the hexagonal close packing. And hexagonal close packing, again we have to see two types. That is hexagonal close cubic packing and cubic close packing. Okay, that is all about the close packing of the solids in case of crystalline solids. Okay. Now we have to see the arrangement of the solids, crystalline solids. So student, you see here, so you are arranging the solids, what will happen, sir? They are found to be closed. But while they are closing, sir, at that time some spaces is to be leftovers. And these spaces that is found to be leftovers, that is, we can say empty spaces is found to be formed. Empty spaces. And these empty spaces, we can say, they are nothing only, we can say these empty spaces, those are formed when the solids are found to be close together. They are said to be your voids. That is, you can say voids, or you can say interstitial spaces. So interstitial spaces are the voids or the living spaces where the spheres are coming to contact with each other in the formation of the crystalline solids. So let us look here, sir. Whenever we have to form the solids in empty spaces, let us look here, sir. I have to take these voids are again two types. Voids are two types. While we are arranging the solids, two types of voids are found to be formed. How these two types are formed? You see, first, if you take three spheres, and in these three spheres, just you have to take another more spheres above of each. Just like you take, let us you to take 3x, we keep this 3x, and above 3x we have to keep above 3 centers of it. Then you will find that some spaces is found to be left over while keeping these 4x, and this space is known as your voids. Because these voids is formed by keeping 3 spheres, so that is, we can say tetrahedral voids. So the tetrahedral voids are found to be formed when the 3 spheres are found to be arranging, and above the 3 spheres the 4th one is found to be present on it. Then the middle space that is found to be formed is said to be a tetrahedral voids. Unlike the tetrahedral voids, if we keep it, just you take 3 spheres, and in these 3 spheres, if we will keep another 3 spheres, then what will happen? Let us look here. So we have to take 3 spheres attached to each other, and in these spheres, let us we have to take another 3 spheres. So you see, whenever we have to take 3 spheres and above it another 3 spheres has to be kept, what is the space is found to be formed? That is known as also octahedral spheres. So let us look here, sir. these octahedral spheres, they are found to be obtained whenever three spheres overlap with another three spheres. What is the space is to be left over? That is, you can say octahedral spheres. And tetrahedral voids, it is octahedral voids, not spheres. Octahedral voids. So octahedral voids is found to be formed when three spheres overlap with another spheres, and tetrahedral voids is found to be formed when the upper sphere is to be surrounded by three lower spheres. Okay. So actually, whenever you have to arrange the crystalline solids, what happens here? There is the spheres is to be left some spaces. What is the space left? Those space you can say interstitial space, or you can say your space are the voids. Once again, if you take the size of the atom and the voids, then what is found to be, if the size of the atom have the radius, size of the atom have radius r, then we can say the tetrahedral voids has 0.225 r. Tetrahedral voids are found to be 0.225 r. So what is the size or radius of a voids? The tetrahedral voids are found to be 0.225 r. Similarly, whenever we put the octahedral voids, here the size of the octahedral voids are found to be 0.414 r. Okay. So if you compare the size of tetrahedral voids and that of the octahedral voids, then the size of the tetrahedral voids is found to be 0.225 r, and size of the octahedral voids are found to be 0.414 r. So it is generally you can calculate the number of tetrahedral voids in a particular solid is generally found to be double that of the octahedral voids. That means we can say the ratio of tetrahedral voids to octahedral voids in a solid is 2:1. Okay. The radius ratio and coordination number. So let us look here, sir. Now we will discuss regarding radius ratio and coordination number. What is radius ratio and what is the coordination number? Radius ratio, you see any ionic solid, they are consist of the oppositely charged ions, that is cations and anions. When these cations and anions come to each other, what happens? They are oppositely charged ions and they are tightly held. Since they are tightly held, so they have to be formed the ionic solids. So in this case, the size of the anions is found to be greater than the size of the cations. Okay, that's why in such a cases, the radius ratio helps us to determine the structure of the solids or nature of the solids. So this radius ratio is the ratio between, that is, you can say, size of cation to that of the size of anion. So the radius ratio is the terms, we can say it is cation size to that of the anion size. Okay. So to get the cation size and anion size, that simply we can say our radius ratio. In this radius ratio, this determines also the type of the structure of the solids. Now you see, let us see, we have to take radius. For example, we have to take the radius ratio of NaC, sodium chloride. Then you can say the radius ratio is equal to size of Na plus ion by size of Cl minus ion. Okay. So as you know that the cation is a small size, anion is a big size. So always the ratio will always remains less than 1 or it becomes maximum 0.99. Okay. So 0.99 is the maximum ratio value will come because the cation size is found to be more than that of the anion size. Next, the coordinate and this radius ratio helps us what type of the structure it is, the compound. Like the radius ratio, next is your coordination number. What is coordination number? Coordination means somebody has to coordinate, someone has 4 friends, means his 4 is coordinating to him. Just like that, a sphere when contact with other spheres, with how many spheres it is attached with, then that we can say it's a coordination number. So coordination number is oppositely charged ions that has to surround to a particular ion, then we can say its coordination is that much. Generally, the solids are found to be coordination number values. Most common coordination values 12, 8, 6, 4, 3. These are the coordination values. But maximum we can found 864. Okay, 864 type of coordination number is found to be more in case of our ionic solids. And this coordination number as well as radius ratio, they are linked. Now let us look here. So we have to find the density of the unit cells. How we have to find density of the unit cells? So why we have to find the density of the unit cell? You see, if we have to represent density of a unit cell, that is rho, then we can say it is mass of the unit cell, divided by volume of the unit cells. Okay, so let us have to find the density of a unit cell in a solitary cells. Whenever we have to find the densities, we have to know the mass of the unit cell and volume of the unit cells. Okay, so let us look here. So first of all, we have to take a solid whose edge length is a, small a, edge length is a. That means its length is a. If it is a in a cubic cell, what will be its volume? Volume of the unit cell will be what? Length cube. Unit cell equal to your a cube. So now look here, that is volume of the unit cell is a cube. But to find the density of a unit cell, we have to know mass of the unit cell and volume of the unit cell. Now let us we have to know mass of the unit cell. What is mass of the unit cell? Mass of the unit cell. Mass of the unit cell equal to mass of that particular unit cell, let us say small m, multiplied with z. Okay. Now the question, what is z here? You see, the unit cell you have to know previously 3 types. That is simple unit cell, body center unit cell and face center unit cell. If it is simple unit cell, then we know we have to calculate the area also. Number of atoms z is equal to 1. If it is body centered unit cell, then you know the number of atoms is 2. If it is face centered unit cell, we calculated that value is 4. Okay. So the value of z is found to be differ what kind of unit cell it belongs. If simple unit cell 1, body centered unit cell 2, face centered unit cell 4. So now you see mass of the unit cell equal to m unit cell equal to small m into z. Again you know that small m equal to n by capital N. Okay. What is n? N is Avogadro's number and capital M is your molar mass. Okay. So in case of the small m, we can put here, sir, what is Na by m into z. So that is mass of the unit cell. So whenever you have to find the mass of the density of the unit cell, mass of the unit cell divided by volume of the unit cell. Mass of the unit cell we have to find out what is it? Na into z by m, and volume of the unit cell is your a cube. That is your a cube. So you see, we have to get the value Na into z, m into a cube. Okay, so that is the formula to find the density of the unit cells. Okay, the structure of the compound. For example, if you see the radius ratio comparison between link between radius ratio and coordination number, what will happen? Radius ratio and coordination number. Let us look here, if the radius ratio will remains from 1 to 0.732, then that coordination number will become 8 and the structure will come cubic. Structure will become cubic type. Similarly, if the range will come 0.732 to 0.414, then the coordination number is 6 and it becomes octahedral type. Okay. Similarly, if the coordination number ratio will come 0.41 to 4 to 0.2 to 5, then the coordination number will come 4 and it is found to be tetrahedral. Similarly, if you come to the ratio is 0.2 to 5 to 0.155, then coordination number is 4 and it is triangular type. So let us look here, students. Radius ratio and coordination number. These two gives us the structure of the compounds. Radius ratio, it is the ratio between cation, size of cation to the size of the anion. What is coordination number? Coordination number is the particular ions has to be surrounded with other atoms. For example, if you take a little example I cite you, sodium chloride. In sodium chloride crystal, each Na plus is surrounded by 6 Cl minus. Okay, so you say the coordination number of Na is 6. Similarly, each Cl minus ion is surrounded by 6 Na plus ions. Coordination number of Cl also 6. So coordination number is opposite charge ions surrounded. The radius ratio, it is the ratio of cation to anion. Okay, so there is a relation between coordination number to our radius ratio. What will the radius ratio respectively coordination number will form like that, and when the coordination number will come, that the structure is found to be like this. So different elements or different compounds will bear the structure of like this according to how they are coordinated, how the structure is formed, and what is the radius ratio, which depend once again the cation size and anion size. So this radius ratio and coordination number will help us to know the structure of the ionic solids.